What initially started as a somewhat crazy idea has now become much closer to reality thanks to Project EcoMobility and to the active support of our partners TNO and Valeo. After 3 years of intensive work in Demonstrator 1 of Supply Chain 3, we have now achieved some promising results to show.
Passing 195, flight level 260. Ethiopian 722, good evening, flight level.
In domains such as aviation, the pilots do not decide on their own which path to take. Every decision is coordinated by the air traffic controller. This way it's ensured that no two planes are on the same path, but collisions are avoided proactively. In road transport, the things have historically been different. A large number of vehicles is moving on the road, making their individual decisions, simply because there hasn't been any affordable and reliable communication and localization technology available for this purpose. However, recently technological improvements like 5G have changed the situation fundamentally. By using high-speed 5G communication and affordable high-precision GPS receiver, it is now possible to create a virtual representation of the situation on the road. Sensors available in modern cars detect the vehicle surroundings, and thus non-connected vehicles can also be included in the situation picture. A central dispatch unit called Road Supervisor then optimizes the traffic and sends recommendations, primarily target speed and lane change requests, to the vehicles under supervision. In the end, the driver, or in case of automated vehicles, the local vehicle controller, has the final decision to follow the recommendation or to reject it due to safety reasons. Since the number of available full automated vehicles with open interfaces is very limited, we needed something to upgrade a normal vehicle and make it useful for our project. Therefore, the vehicle kit was developed, which converts any given vehicle into a connected vehicle within 30 minutes.
As a key industrial partner in the EcoMobility project, Valeo plays a leading role in Supply Chain 3, which focuses on intelligent connectivity. Valeo's primary technical contribution is the development of the TCU prototype. The TCU, or the Telematics Control Unit, provides 5G capabilities, V2X capabilities, and high precise positioning capabilities to the demonstration vehicles used in this project.
Additionally, an antenna box has to be mounted on the rooftop and a tablet PC has to be attached on the windscreen. And then, after some cabling, the connected vehicle is ready to drive. Optional part of the vehicle kit is a affordable radar sensor, which can be mounted using our modified license plate holder. This is the Road Supervisor setup. It essentially consists of a powerful industrial computer which receives the data from the connected vehicles using its 5G modem. For best network performance, the external 5G antenna has been installed. On the left side is a notebook which is responsible for maintaining and visualizing the shared world model. On the center screen we see the output of the trajectory optimizer, and on the right hand side we have a notebook which can be used to run a traffic simulation to stimulate the road supervisor with simulated data. The scenario is kept simple in order to implement it on a public road in everyday traffic. 4 connected vehicles basically block the motorway while a connected emergency vehicle is approaching from the rear. It is expected that the connected vehicles receive recommendations resulting in the quick passage of the emergency vehicle, while maintaining safe distances between all vehicles all the time. These are the vehicles participating in the test drive. The virtual vehicle automated drive demonstrator represents the role of the emergency vehicle in the scenario. Now the vehicles are on the highway in a proper formation and the tests can begin. All vehicles are equipped with a tablet PC running the vehicle software. It basically consists of a large tachometer showing the current and the recommended speed. Lane changes are indicated using an icon on the screen. Additional voice commands are sent to the in-car radio system via Bluetooth. In manually controlled connected vehicles, it is the test driver's responsibility to follow the speed recommendations as close as possible. Furthermore, lane changes must be done swiftly after checking with surrounded traffic. In the automated driving demonstrator, speed control, lane keeping and lane changes are done fully autonomously by the in-vehicle controller. However, for safety reasons, the test driver has to approve every lane change by activating the turn signal. Now the scenario has been completed successfully. The emergency vehicle, which initially started at the end of the convoy, is now in a leading position.
TNO's shared world model creates a unified, real-time view of the environment by fusing data coming from multiple connected vehicles, roadside sensors, or other connected infrastructure. This shared world model allows for earlier anticipation and detection of other traffic participants which would be otherwise occluded from the vehicle's point of view. And especially when this world model is shared between connected vehicles, it allows for maneuver coordination, which can significantly improve traffic flow, especially during complex maneuvers.
A snapshot of the shared world model is taken every 100 milliseconds. Then the trajectory optimizer creates and improves a set of trajectories for all vehicles under supervision using a genetic algorithm. The optimizer takes the position and the current vehicle speed as input and then calculates the optimized speed and lane for every vehicle under supervision. Numerous constraints apply to this optimization, for example, the speed limit, the continuity, the safety margins, vehicle priority, traffic loss, and the driving comfort, to name just a few of them. In the final step, recommendations for all connected vehicles are derived and sent to the individual vehicle where they are shown on the screen for the driver. In automated vehicles, the recommendations are directly applied by the vehicle controller. Here is a time-lapse of a recorded test drive. Because of the traffic situation, only small differences in speed were possible this day. Therefore, the maneuver takes a relatively long time. It can be seen how the full automated emergency vehicle in red slowly overtakes the other connected vehicles shown in green. All other vehicles are colored yellow. Our demonstrator shows that the concept of the Road Supervisor is feasible with affordable current technology, and it can provide useful recommendations for both manually driven and automated driven vehicles. Obviously, it's still a prototype, but it has now a much higher TRL level than it had before Project EcoMobility.